Last episode we built the house, the phishing URL detector, seed 42, PRAAOC 0.958, and it just worked because phishing and benign were close to balanced. But the SOC's worst day doesn't look like that. Ransomware beacons are under 2% of the flow records, so you do the obvious thing. You point XGBoost at the table and hit train. The model comes back, accuracy says 98%, everybody nods, and at the default threshold, it catches fewer than half the ransomware beacons. The rest phone home to the C2 all night and nobody is paged. This episode is about why just train normally quietly undercatches the rare class, and the one line that decides how many you catch. First, the misconception stated plainly: more data of the boring class makes a better detector. It doesn't. We have 20,000 net flow records, and under 400 of them are beacons, well below 2%. I'll draw them as dots, a wall of green, a thin red thread. The model that minimizes average error on this picture is the model that says normal to everything, and it's right about 98% of the time. Accuracy rewards the lazy answer. Here's the mechanism nobody shows you. XGBoost learns by chasing the gradient, the direction that reduces total loss fastest. With roughly 14,700 benign gradients pulling one way and under 300 attack gradients pulling the other, the benign votes outnumber the attack votes about 50 to 1. Every tree split is decided by a near unanimous crowd that has never been hurt by a missed attack. The rare class isn't ignored on purpose, it's outvoted. So you train the default model and read the confusion matrix. Of 97 real beacons in the test set, it catches 43 and misses 54. Recall 0.44. That's the number that kills the misconception. The model will figure out the rare class on its own. It won't. It found the easy half and stopped because the loss surface stopped rewarding it. The fix is a single hyperparameter, scale pose weight. It multiplies the gradient of every positive example by a constant. Set that constant to Takeover pose. Here about 14,700 over 290, roughly 50. And now one attack mistake hurts as much as 50 benign mistakes. The crowd is balanced. This busts the belief that fixing imbalance means resampling, copying rows, or summoning synthetic attacks. You don't touch the data, you reweight the math. Retrain with scale pose weight set to about 50 and read the matrix again. 57 of 97 beacons caught, recall 0.59, misses fall from 54 to 40, 14 more beacons pulled out of the dark. That's the headline. Recall 0.44 to 0.59 from a single assignment. Now the honest bill, and it's bigger than the tutorials admit. Precision falls hard, 0.93 down to 0.55. Catching 14 more beacons means flagging a lot more benign flows, and the false positive rate climbs from 0.1% to a full 1%. And here's the part most courses hide. PRAIOC, the ranking quality, barely moves, 0.63 to 0.59, essentially flat. Scale pause weight did not make the model smarter at telling a beacon from a benign. It slid the decision boundary down the same precision recall curve, buying recall by spending precision. So this isn't a free lunch, it's a deliberate trade, and you make it because in ransomware, a missed beacon costs far more than a false alarm. One discipline before we touch code: set scale pose weight first, before max depth, before eta, before anything. Tuning tree knobs on a model that can't see the positive class is polishing a telescope pointed at the wall. Rebalance the gradient, then tune. Open arrow 3 imbalance scale pause weight.py. Same shape as Epo2, seeded data built in code, no downloads, but the weights are deliberately brutal. Lines 1 to 14, build the world, make classification, 20,000 rows, 11 features, 9 informative, weights 85 0.015, class SEPSO13 random state that's 11. Then rename the columns to real beacon telemetry, beacon interval var, dest port entropy, tells J3 rare, C2 ASN rep. So the feature names mean something to a detection engineer. Stratified split keeps the rare beacon rate in both train and test. Lines 16 to 18 compute the knob from the data, never hard-coded. SPW, y train volatile handles 0. Sum, Boltaribu train Boltaribu threshold. Sum, the count of benigns over the count of beacons, print it. On this seed, it's about 50. That print is the same number you will see on screen and in the matrix title. Lines 2031. Train both models, identical everything, same max depth, same eta, same n estimators, same seed. The only difference is scale pose weight 1 versus scale pose weight S poly. That's the controlled experiment. If two things differ, you can't attribute the win. Here exactly one does. Lines 33 or 44, score honestly. For each model, predicted labels at the default 0.5 threshold, then recall score, precision score, and average precision score. That's PRAOC on the held out beacons. We do not print accuracy. Episode 4 is the whole episode on why that number lies, and we're not going to flash it here and undo our own lesson. Lines 46-61, draw the hero. Two confusion matrices side by side with confusion matrix display. Default on the left, weighted on the right. The missed attack cell, bottom left, annotated on both. So the drop from 54 misses to 40 is impossible to miss. The printed matrix line and the matrix cell counts come from the same arrays, figure equals terminal by construction. So, one knob set from the data turns a detector that catches fewer than half the beacons into one that catches a clear majority, and the bill is the precision you deliberately choose to spend. PRAUC barely moved, and that's the real lesson. This knob picks your operating point, it doesn't make the model smarter. But notice what we leaned on the whole episode. Accuracy was useless and we never even printed it. Next episode, the PE malware classifier that scores 97% accuracy while catching nothing, and why PRAUC is the only number our SOC should trust. Accuracy lies, we're about to prove it.